Ever wondered how software systems are designed? Today, you are in for a treat. We're diving into the fascinating world of object-oriented design, or OOD. It's a strategy in software design that's all about objects, not actions, and data, not logic. It's how we organize a system around these objects, rather than functions or procedures. This approach is a key part of the object-oriented programming process, implemented using languages like Java, C++, Python, and others that support OOP paradigms. Now, let's talk about the key concepts of object-oriented design. Objects and classes, which are the heart of OOD, encapsulation, the principle of bundling data and methods into a single unit, inheritance, which allows for code reusability, polymorphism, allowing methods with the same name but different implementations, and abstraction, the art of hiding complexity while exposing only what's necessary. Stick around to learn how these concepts come together in the design process. First off, let's delve into objects and classes, the building blocks of object-oriented design. Imagine objects as real-world entities that encapsulate both characteristics and behaviors. For example, consider a car. It has characteristics like color, model, and brand, and behaviors like accelerating, braking, and turning. In the world of object-oriented design, the car is an object. Now, where do these objects come from? They're created from a blueprint known as a class. A class lays out the attributes and behaviors that every object of that class will have. So, in our car example, the class might define attributes like color, model, and brand, and behaviors like accelerate, brake, and turn. Classes are like cookie cutters, and objects are the cookies. Each cookie, or object, may have different details, chocolate chips, raisins, or nuts, but they all share the same basic shape defined by the cookie cutter, or class. Let's take a more technical example. Imagine a class called customer. This class might define attributes like name, address, and order history, and behaviors like place order, update address, or view order history. Each individual customer is an object of the customer class, with their own unique name, address, and order history. It's important to note that while every object is an instance of a class, not all objects of a class need to be identical. They can have different values for their attributes. So, while all objects of the customer class will have a name, address, and order history, the specific details, the customer's actual name, their particular address, their unique order history, will vary from object to object. In essence, classes provide structure. They're a template for how objects should look and behave. Objects, on the other hand, are instances of these classes, carrying their own unique values and leveraging the behaviors defined by the class. Understanding objects and classes sets the foundation for the rest of the object-oriented design process. Now, let's move on to encapsulation and inheritance, two key principles of object-oriented design. First up, we have encapsulation. Picture this. You've got a bunch of data, and you've got a bunch of methods that manipulate that data. What do? You bundle them up together like a tidy little package. That's encapsulation for you. But it doesn't stop there. Encapsulation also throws up a protective barrier around your package. It restricts direct access to some of the object's components. This is like having a security guard at your door, preventing any accidental or unwarranted changes to your data. In other words, encapsulation promotes data integrity and security, which are vital for any robust software system. Now, let's sail onto the shores of inheritance. Inheritance is the principle that allows a class to inherit characteristics from another class. It's akin to a child inheriting traits from a parent. In the world of object-oriented design, the class that inherits is called the subclass or derived class, and the class it inherits from is the superclass or base class. This principle is incredibly powerful as it promotes code reusability. Instead of writing the same code over and over again, a subclass can simply inherit the relevant characteristics from a superclass. It's like having a magic wand that can duplicate the desired traits with a simple wave. But it's not just about duplicating code. Inheritance also allows us to establish a hierarchical relationship between classes, which can help us organize our code better. It's easier to understand, manage, and modify. In a nutshell, encapsulation and inheritance are like two sides of the same coin. Encapsulation helps us bundle data and methods into a cohesive unit, maintaining the integrity and security of our software systems. On the other hand, inheritance enables us to reuse code efficiently and organize our classes in a logical hierarchy. These principles enable us to design robust and reusable software systems. Next up, we have polymorphism and abstraction, two more pillars of object-oriented design. Polymorphism, derived from Greek words meaning many shapes, is a principle that allows classes to have methods with the same name but different implementations. Picture a simple action, like drawing. An artist might use a pencil, a brush, or a digital stylus, yet the action remains the same, drawing. In our coding world, the drawing method could be implemented differently depending on whether the artist object is a pencil artist, brush artist, or digital artist. That's polymorphism in action. Polymorphism can be achieved through method overriding, where a method in a derived class has a different implementation than the same method in the base class. This is like a jazz musician taking a classic tune and giving it a fresh spin. Similarly, method overloading allows multiple methods to have the same name, but different parameters. It's like ordering a pizza. You say, "I want a pizza," but the type of pizza you get depends on the additional parameters you provide, like pepperoni, vegetarian, or extra cheese. Next, let's talk about abstraction. Abstraction is like an artist drawing a stick figure. The figure doesn't have all the details of the human body, but it's enough for us to understand that it represents a person. In the same way, abstraction in programming means hiding the complex reality while exposing only the necessary parts. It's about simplifying complexity, hiding unnecessary details, and showing only essential attributes of an object. Think of a car. To drive it, you don't need to know how every single part works under the hood. You just need to know how to operate the steering wheel, pedals, and perhaps the gear shift. That's abstraction. With these principles, polymorphism and abstraction, we can create flexible and manageable software systems. Much like an artist uses different tools and techniques to create a masterpiece, we use these principles to design and build efficient, effective, and elegant software solutions. And with these principles, we can create flexible and manageable software systems. Now that we've covered the key concepts, let's walk through the process of object-oriented design. Object-oriented design is akin to crafting a blueprint for a building. It's the plan that guides the construction, ensuring that the final product is robust, efficient, and easy to maintain. The process begins with identifying the objects. Think of objects as the building blocks of your system. These are usually derived from the specifications provided, often represented as nouns in use cases or requirements documents. The objects you identify will form the backbone of your design. Following the identification of objects, we move on to defining classes and their relationships. Classes are like the blueprints for objects, outlining their attributes and behaviors. Relationships between classes are also established during this step. These relationships could be associations, aggregations, or compositions, each defining how one class relates to another. Next, we establish interfaces and inheritance structures. Interfaces are like contracts that define what methods an object exposes, while inheritance structures determine how classes inherit attributes and behaviors from each other. This step is akin to deciding how rooms in a building will be connected and what features they will inherit from the overall architectural style. Once the structure is in place, we design the interactions. This step involves determining how objects will communicate with each other, much like designing the flow of traffic within a building. It's all about defining how the different parts of the system will work together to accomplish tasks. Finally, we plan the implementation. This is where we consider how data will be stored and retrieved, and how objects will be created and managed in memory. It's like deciding where to place the plumbing and electrical systems in a building, ensuring that everything runs smoothly beneath the surface. Following this process helps us design software systems that are efficient, scalable, and easy to maintain. It's a journey from abstract concepts to a concrete implementation, with each step building upon the last to create a comprehensive design. So, roll up your sleeves and dive into the captivating world of object-oriented design. We've covered a lot today, but let's quickly summarize the key points of object-oriented design. We started with objects and classes, the building blocks of our design. These represent a combination of data and methods. Then we delved into encapsulation, which is about bundling data and code into a single unit while restricting direct access to prevent accidental data modification. We also discussed inheritance, a feature that allows a class to inherit characteristics from another class, promoting code reusability. We explored polymorphism, which allows classes to have methods with the same name but different implementations. Lastly, we touched on abstraction, which is all about hiding complexity and exposing only the necessary parts. We also walked through the process of object-oriented design, starting with identifying objects, defining classes and relationships, establishing interfaces and inheritance structures, designing interactions, and finally, planning for implementation. Understanding and applying object-oriented design can elevate your software development skills to new heights. So keep practicing and happy coding!